Okay, so here we're going to go over this problem involving exponential growth. So what we have here, it says in the initial stages, a bacteria culture grows approximately exponential. If the number doubles after 5 hours, what proportion of the original will be present after 6 hours, right? After 12 hours. Okay, so here we have a very typical, right, exponential growth, right? So I know it's growing because something is doubling, right? It's getting bigger after 5 hours, right? So exponential growth, so the type of growth that we see looks like something like this, right? If we think of, so we're dealing with time, so usually, right, if t is our horizontal, right, t starts at 0, it doesn't make sense in our applications to have negative t. So it looks something like this. Now, avoid when dealing with exponentials, commonly I see they'll try to break down, oh, if it doubles every hour, every 5 hours, what happens in 1 hour? This grows exponentially. So, in other words, if you are thinking about it, like I'll break down, like, oh, what happens the growth in 1 hour if it doubles every 5? That's a linear type of growth, right? Which is not the same. It's a different behavior, as we've seen, right? Linear has this growth here. Right? So you will not arrive at the same type of conclusion if you think, all right, if it doubles every 5 hours, let me see what happens in 1 hour by this type of math. But that's linear thinking, and what we have here is exponential. So instead, what we're going to do here is we're going to take a look at our function, right? The notation, a common notation is this, right? A at some time t is a naught e to the kt. Right? Okay. Where t is some value of time, right? A naught is a constant, so this is our initial amount. Sometimes given as an actual number, but sometimes it is not, and that's okay, right? If you notice here, this does not tell me what it just says in the initial stages of bacteria culture grows approximately exponential. Right, I have no idea how much I've started with, and it is not really necessary, right? Here we're going with percentages based on some original number, right? Doubles, triples, right? It's all going to be a number compared to some initial amount that we'll leave as a naught, right? Some constant. Okay, so that won't affect my calculations in the sense that we'll just kind of carry along the a naught. Okay, so K is usually our growth rate, right? If it's positive, it's growing. If it's negative, it's representing decay. Here, K is some positive value, right? Because it's a growth function, right? If we were dealing with decay, which we'll do in the next example, we will have some negative value, right? But for now, here looking at this, we say, okay, well, these problems are usually in 2 steps, right? Or sometimes 3, and here they ask us 2 different values, right? The initial value, the initial part of this problem is to find what k is, right? And the way we do that is we use this initial conditions that they give us, right? Or I should initial statement where it says the number doubles after 5 hours. So the amount, so what that means, right? The way I interpret that mathematically, right? The amount doubles. So that means that after 5 hours, well, what amount? The initial amount. Whatever I started with is now double. Okay, so that's how I interpret that graphically. But also a of 5 is the function, the exponential growth function, where I plug in 5 for t, right? So now I have these two, they're equal to each other. So now what I can do is I have, all right, well, let me go ahead and set these equal to each other. Oh, excuse me, e to the 5k. Okay, all right. All right, and now notice here right away, right, that initial amount, that simplifies to 1, and really we have 2 equals to e to the 5k, which is why I said that the initial amount is not important, right? All these we do relative to whatever that initial amount by saying things like it has doubled or it has grown by 20%, etc., right? Those are, and again, that's a trademark of exponentials, right? We think about it as percent change. All right, now using techniques that we learned solving equations, right, involving e, we can take the natural log of both sides. All right, so if I do that, ln of both sides here, all right, that 5k now becomes a coefficient, so we get ln of 2 is equal to 5k ln of e. All right, and this is 1. All right, so I can divide 5 by both sides, and then I get this for my value of k. Okay, so now I have my model, right? This is actually the hardest part, right? Once I found this, I can go to my function, right? K, so t, and then k, or let me write it how it is. K is ln of 2, and then here we're going to have times t times 1/5, so we get t over 5. All right. Okay. All right, and we can actually simplify this further using properties of logarithms and the inverse property. I can rewrite this as ln of 2 t to the 5th, and ln of 2 is the inverse property, so I get a to the 0 2 t over 5. All right, and now we have our model. All right, and like I said, this is the hardest part, right? We haven't addressed the problems that they ask us, like what will the original, how much of the original amount, or what proportion, I should say, of the original amount will be present after 6 hours and after 12 hours. Okay, so that is actually quite easy, right? If I want to find out, well, how much is present after 6 hours, well, that's simply a of 6. Right? Again, I don't know the initial amount, but it's a proportion of the original amount. Plug in 6 for t, and 2 to the 6/5, right? So here we'll have 2 raised, use that caret for the power. Be careful here. Make sure you have a parentheses, raised to the 6/5, and we have 2.2, well, let's say 30 of the initial amount. Excuse my sloppy writing here. All right, so the way you interpret that is after 6 hours, you have twice the amount. You essentially have 230%, right? The way you interpret that, right? That's the proportion, right? The decimal. 230% of the original amount. So it's more than double, right? Doubled and an extra 30% on top. All right, so that's after 6 hours. All right. Now, after 12 hours, again, resist the urge to just simply double that, right? That is not how that is going to work, right? That, what you're thinking of is a linear growth, right? This is exponential, and we'll see actually, right? It is much more than twice this, right? If we simply say, oh, 6 more hours, let me just double that, that'd be 4.6 hours, or 460% of the original amount. But let's take a look at what the actual result is going to be. 12 over 5. So now let me go again up here, 2 raised to the 12 over 5. Hit enter. All right, and notice here that it is actually more than double what it was at 6 hours, right? That's that exponential growth at work. Okay, so after the 12 hours, we actually have 527, or 28, rounded properly, 28% of the original amount. Okay, all right, and that is how you work with exponential growth. Now, a couple things as you work through these. All of these problems are going to be, all these word problems, exactly the same. They're going to give you some initial type of information where it says something doubles after 5 hours, or it grows by 30%. It doesn't necessarily have to be double, right? And you're going to use that information to find that value for k. Right? And then once you do that, once you find the value for k, then whatever they want you to find after some specific time, that's actually the easy part, right? That should simply be just plugging in values that you are trying to find. All right, thank you.